Welcome to Study Loop.
In this problem, we have a hemispherical bowl, and we have a rock that we can treat as just a particle, point particle, that slides from A to B along that bowl. We're given the mass of the rock, and we're given the radius of the hemispherical bowl. We're also told the magnitude of the work done by kinetic friction. What's its sign? Positive, negative? You might have a sense it should be negative, and that would be correct. But let's see where that comes from. Let's look at an infinitesimal displacement along the path A to B. By definition, this is tangential to the curve. Now, you know that if a book is sliding on the floor to the right, kinetic friction is going to be in the exact opposite direction to the left. No different here. Absolutely no different. So let me redraw this. So here is ds vector, and then here would be kinetic friction. 180 degrees difference between the two vectors. Now, you might say, okay, that's understandable. How can you justify the negative sign? Where does that come in? Well, remember there's a formula for work. When you have a constant force, and that means constant in magnitude and constant in the angle it makes with the displacement. Now, we can't apply that formula for the whole path because though the kinetic friction will always be 180 degrees from the displacement no matter where you look, the magnitude of displacement is changing. Magnitude of the kinetic friction force is changing at every instant, so it does not apply. So we can actually do it for one point at a time, which by definition, you only have one angle, and you just have single force. It's not changing. It's not a finite path, it's an infinitesimal path. So the work done for that infinitesimal path, what are the ds, is Fk, magnitude of the force, magnitude of the displacement, cosine 180 degrees. And we know cosine 180 is equal to -1. And that will be true at all points. You could do this at every single point. Fk changes, but there's always cosine 180, so they're all negatives. So just adding up all negative values to get the work done by Fk is equal to minus 0.22 joules. So we know the negative sign. All right, now part A, subpart I wants to know the work done by the normal force. Now let me draw another infinitesimal displacement. I'll call this 1, and I'll make this one 2 now. Again, tangential to the curve, in this case a circle. Now, n perpendicular to ds at all points. You might say, why is that? Well, think of it this way. Think of this arrow as defining a surface of an inclined plane. You did many a problem where you had to draw free body diagrams for objects on inclined planes. Weren't those normal forces perpendicular to the incline? So that means they're going to be perpendicular to ds1 and ds2. Now remember though, these are tangential to a circle. So that means the normal force, if they're perpendicular to the tangent, that means they're radial. That means they will point to the center of the circle. This guy right here. So I'll call this N1. This angle is 90 degrees. This is N2. This angle, 90 degrees. Right now, all we care about is 90 degrees, but we do need that it is pointing to the center of the circle a little later. The normal force will change, as we're going to see, at every instant, just like the kinetic friction force changes at every instant, every point. So we cannot use FD cosine theta for the whole path, but we can do it point by point. So dWn n ds cosine 90 degrees, but cosine 90 degrees is 0. So when we look at every single point, add up every point, that's what integration would be for. Add up, you'd have an infinite collection of zeros added together. Well, what's that? 0. So Wn, 0 joules. So that's the work done by the normal force, 0. Subpart 2 wants to know the work done by gravity. And this can be calculated 3 different ways. I'm only going to show you the one they intend. You could look at it, the fact that gravity is a conservative force, it means the work done is path independent. So what does that mean? That means find the value for the work between 2 points for one path connecting those points. You got it for all paths. So simplest here would be A to the center point to B. You could do that. Second approach is using potential energy. Now, technically, 1 and 2 are connected because you can't have potential energy if you don't have path independence of the work, which comes from being a conservative force. Now, remember for gravity, gravitational potential energy, and I'll use U. You might use just PE, but I'll use U. MGY. You might use H here, MGH, same thing. So we're going to use that. Let me draw my bowl again, somewhat, a little smaller, but it serves the purpose. With potential energy, you always got to define your 0. So this is my 0 line. That means Y values above are positive, Y values below are negative. Now this may not, it didn't really come out to be the lowest point, now did it? Okay, I just missed a little bit. And let me put it in. All right. So this is point B. YB will be minus R, distance R, but it's below the 0 line. Point A is on the 0 line, so YA is 0. So now really, the connection between work and potential energy is that you define potential energy in terms of the work. So really, this is a definition. UB minus UA. That difference is defined as minus the work done as you go from A to B. That's the definition of it. Now, we know UA is 0 because YA is 0. So we get mg minus R is equal to minus WAB. So that means WAB is mgr, which putting our values, 0.2 kilograms, 9.8 meters per second squared, 0.5 meters, 0.98 joules. That's how much work gravity does. Now, there is a third way of doing this, and that is using line integration. Nothing special about that. You may have seen it, or if you've not seen it yet in the calculus class, you will see it. You will see it coming up in your near future. This basically doesn't make any use of any property of the gravitational force, and you basically have to look at the work for. You have to do those dWs. You have to add up the infinite collection of dWs for gravity, just like you would have to for friction if you were going to do it that way. That's what's called a line integral. You're looking at, you're doing your infinitesimal displacements along here and calculating the work for each of those. So really nothing special, but not important for our purposes here. Part B wants to know the it actually wants to know the speed at point B. So we go to the work kinetic energy theorem. W total is the work done by kinetic friction plus the work done by normal force plus the work done by gravity is equal to change in kinetic energy, which is Kb minus Ka. But we know Ka is 0. It started from rest. We're told that. So Kb, which is equal to 1/2 m Vb squared, is equal to Wfk plus Wg. Solving for Vb, square root 2 over m Wfk plus Wg. And we can put in our values to get what the speed is at B. 2 over 0.2 kilograms minus 0.22 joules plus 0.98 joules. And this comes out to be 2.8 meters per second. That is the speed at point B. Now, part C wants to know of the three forces that act, are any of them constant? Well, let's look at it. Normal force. We can see just from our diagram that as a vector, directionally, it does not make the same, it does not point the same way in space. You know, if you want to think of it in terms of the angle it makes with the horizontal, this has got a greater angle than this. So it's telling you that the vectors are not the same. You could not put one on top of the other and say it's got the same arrow. You don't have that. So certainly changes direction, but what's really more important than that is the magnitude. What type of motion is this object undergoing? Circular motion. So let me draw a point here. Here's the normal force. Here's the gravity. Now, this is toward the center, so I'll make this the plus r direction. Remember, you have to have something in circular motion, you have to have a net force toward the center. Now, let's not forget that I can break this gravitational force into a radial component and a tangential component. Tangential component serves to speed this object up. It goes from rest to VB. That's the maximum. This is FGR, the radial component. And remember, this is our center over here. So F net R N minus, I'm going to put here just the magnitude of the radial component minus, because it's in the opposite direction. We'll, in the last part, we'll actually do the specific point, or one specific point. And this has to equal to mv squared over r. This is for any point. But think about what goes on here, what goes on with n. V we know is increasing. This tangential component causes it to increase. It goes from 0 to something. B is the fastest of all points. And that's because of this. So this is increasing. Remember, the centripetal force is this whole thing, n minus the magnitude of the radial component of the gravitational force. This is the centripetal force. But this net has to be toward the center. Can't all of a sudden become 0 or negative, then you can't turn. Can't turn a circle. You don't have a circle then. Now, so this is going up. The component, the R component of the gravitational force is also growing. At all points, it's got an angle involved. But when you're at the very bottom point, it's the radial component for the gravitational force is the whole weight, mg. Well, it's technically minus mg to be precise, as you'll see in the next part. But it's growing. So when you solve for n, mv squared over r is growing because v is growing. The magnitude of the R component of the gravitational force is growing. So n is growing. Has to. This guy growing, he's got to grow. Because you got to have the centrifugal force to turn this object at its higher speed. Okay, so that's why that's out. Let's look at kinetic friction. It's always 180 degrees from the ds at that point, but the ds's vectors are all changing. They're tangential to the curve as you travel from A to B. So this changes direction. And magnitude, you might say, well, why does it change magnitude? Well, what's the formula for kinetic friction? UKN. Well, we just said n's changing, so kinetic friction has got to change also. Gravitation, all points, it has same direction, always down, and same magnitude. At all points, always straight down, always mg in magnitude. Done deal. So this is the only one that's constant, gravitation, gravitational force. Everybody else changes. Now let's do specifically this type of work for the point B. That's not very good. Okay. So we have normal force, I call it NB. We have the weight, mg, plus r direction, so it's going to be toward the center of the circle. So F net r, NB, minus mg, mvb squared over r. So solving for NB, mg plus vb squared over r. And this is equal to 0.2 kilograms, 9.8 meters per second squared, plus 2.8 meters per second, that whole quantity squared, over 0.5 meters. And this works out to be 5.1 newtons. That's the normal force at point B. That will be the largest because it's got everything going against it. It's got the maximum speed you can have, and the radial component, the magnitude of the radial component of the gravitational force is its maximum. There's no angle involved. It's the full weight, mg. There's no cosine or sine or whatever to reduce that. So this is the maximum you'd have. And that is no problem.